Hello everyone, this is Zhao from IHAP Beijing. Today I'm going to talk about Reactor antineutrino anomaly in light of recent flux model refinements. Okay, here is our outline. I will introduce our motivation, new calculation of IBD yields for different models, the fitting method, and the fitting results for based on reactor rates and reactor fuel evolution data. Then we will test the best fit model. And at last, I will summarize the concluding remarks. Here is part one, the motivation. Reactor antineutrino anomaly, as known as RAA, is introduced a decade ago in this reference, which illustrates a deficit of event rate between experimental measurement and model prediction. We use reactor experiments data to test RAA for different models. Here are the models we considered in this work. In this work, for the reactor experimental data, we consider both reactor rates data and the fuel evolution data. Here is part two, the new calculation of IBD yields for different models. In theoretical calculation, we use two different methods to obtain the theoretical reactor antineutrino spectrum. One is called the conversion method. It works on converting measurement, the measured beta spectrum into neutrino spectrum. Here, these figures show how to convert AO beta spectrum into neutrino spectrum. It goes from the high energy range to low energy range, using virtual branches to fit the measured beta spectrum. And the other one is called the summation method. It is based on database inputs to sum all the decay branches. Huber-Muller model might be the most famous flux model for us, which is obtained mainly based on conversion method. In Huber-Muller model, they think all decay branches are allowed. Then if we consider the forbidden transition in this reference, a model abbreviated as HKSS model is obtained. And we can see from these two figures, comparing with a Huber-Muller model, the HKSS model can partially explain the shape anomaly. In recent Kurchatov Institute measurement, they find with the assumption of the unchanged uranium plutonium-239 beta spectrum, comparing with the AO measurements, the Ki measurements indicate the reduced uranium-235 beta spectrum. With this correction, in this reference, they have considered the Ki model. They even think about the converted uranium-238 spectrum. And we also apply Ki correction to the HKSS model's uranium-235 spectrum directly to obtain a new model. And we call it HKSS Ki model. EF summation model is calculated with summation method based on database and pandemonium-free data, whose rate is consistent with diabase with only 2% deviation. Here is a summary of the model in our work. We have considered both conversion models and summation models. The conversion models, we consider the Huber-Muller model as a benchmark, which converted from the AO measurements and exists reactor antineutrino anomaly. With the consideration of the forbidden transition, HKSS model can partially explain 5 mega electrovolt bump with new KI measurement instead of AO measurement. KI model and HKSS model, HKSS KI model came up. While for the summation model, we only consider EF summation model for now. Reactor event rates are usually expressed as a physical quantity called IBD yield, as known as cross-section perfection, which is the integral of the products of the IBD cross-section and the neutrino spectrum. And we can say there are two main reasons to affect the value of the IBD yields. The first one is choice of the IBD cross-section, and the second one is the integral energy range. For the IBD cross-section, we consider the first order Vogel-Bacon cross-section with PED 2020 input, especially for the updated neutron lifetime. Here is a comparison between the zeros and the first order IBD cross-section. And for the integral range, all the models in our work give the spectrum below 8 mega electrovolts. However, only EF model gives a high energy spectrum. And thus we consider the EF model's high energy spectrum with 100% uncertainty for all models. From the right figure, we can say this approximation in high energy range is reliable. Note that the contribution above 8 mega electrovolts is very small. Here are the results of our new calculation comparing with the original ones. The part 3, our method of analysis. How we treat the systematic theoretical uncertainty might inspire different fitting method and results. For now, there exist 3 main methods concerning this situation. The method A is used in these 2 references. They use a total covariance matrix with a combination of the experimental uncertainty and the theoretical uncertainty. Here, the theoretical covariance matrix is a strongly correlated one, which may suffer the statistic puzzle called the Peirce-Pernet puzzle. As for the Peirce-Pernet puzzle, we can give an example. If 2 numbers with high correlated uncertainty, the best fit average of both of them can be lower than both of them, which may be caused by the improper combination of experimental and theoretical matrix, or the traction of the data space. And we also find that in this reference, they consider only the experimental part. And in the final fitting result, they have added a global theoretical uncertainty by hand. However, this theoretical uncertainty is hard to obtain. In the recent work, we find the authors prefer to consider the theoretical uncertainty with nuisance parameter, or should say with the Potem. It's a smart way to separate the minimization of the physical parameter and the nuisance parameter. And in this situation, the Peirce-Pernet puzzle is avoided. And the method C is adopted in our work. Here is a part 4, the fate of reactor rates and evolution data. We first fit the reactor rates taking Hilbert-Muller model as our benchmark. The rate deficit decrease compared with the work half decade ago. With different IBD yields and different fitting method, the RAA is decreasing from the 2.8 sigma to 1.9 sigma for now. For the fitting results for other models, we can find the deviation of EF model and HKI model and HKSS-KI model are less than 1 sigma, indicating no anomaly for these three models. We also consider the fitting the Furrow evolution data. We use a linear relationship description of the IBD yields. In this slide, we show the fitting result about the average IBD yield and the slope. There is an exist 3 sigma for Huber-Muller model and HKSS model. While the rest 3 models agree with the evolution data, both for both the fitting of the average IBD yield and the slope. When applying renal data, the similar results can be also obtained. Let's move to the part 5, the best fit model. Considering the squared term in chi-square test, the test only shows the size of the deviation. If you want to rely on both sides and the sign of the deviation, we need to form a transformed data in this equation, the XA mode. It might be a Gaussian distribution, and we also apply Shapiro-Wilk test to test if it is a Gaussian distribution or not. And then we use the sign test and the classical KS test, the CVM test, and the AD test. We also consider the powerful statistic tests in this reference based on likelihood ratio. Here is a CDF of the reactor race data and the CDF of the evolution data. And the black solid line is the CDF of Gaussian distribution. This slide shows the results of the statistic test. On the left is the CDF of the combined data. According to the test of the combined data, we take the EF model is a better summation model, and the KI model is the best conversion model. And here's the part. Here is the last part, the summary. We have updated IBD yields in our work. We also consider the influence of different fitting methods. The RAA, combining both of them, the RAA decreased from 2.8 sigma to 1.9 sigma for Huber-Muller model. And for the best fit model, EF model is the best summation model, and the KI model is the best conversion model. KI measurement can pull down the rate deficit, which indicates that the RAA might originate from the misnormalization in AO measurements, and it needs other experiments to perform. Our work is mainly concerning about the rate anomaly, and for the shape anomaly, it's not solved in our work for now. Thanks. That's all. Thanks.